some more jargon, and then I'll show you one fundamental way in which linear transformations separate themselves from regular functions. Yeah, I'll say more about that in a minute, but let me give you first some jargon. Okay, so first of all, we're going to say that the linear transformation is one-to-one if different vectors in the domain have different images. Okay, so here we have our domain, here we have our range. So a transformation is one-to-one if I pick two, oh, that is the range, I forgot about it. So if I pick two vectors u1 and u2 in the domain and I look at their images, those images are also going to be different vectors. Okay, so in order, let's look at it from the other point of view. A function is not one-to-one if you can find two vectors in the domain that have the same image in the range. Okay. Now, another piece of jargon is that a linear transformation is said to be onto if its range and its codomain is the same. In other words, if I pick up all possible vectors of Rn, which I can always do, and I look at all their images, I'm not covering up just a portion of Rm, but I'm going to cover the whole of Rm. Okay? So one-to-one means one vector on one side, another vector on the other side, everything is different. Onto means I should be able to pick up everything in the codomain. So the range and the codomain are going to be the same. Now, these two definitions lead to a very surprising, or what should be a very surprising and exciting property about matrix transformations. Okay, it's going to almost look like magic, the strange kind of things that we're going to see, because we're not used to it. Okay, but in fact, there is no magic here. So the idea is the following. If we have a linear transformation from Rn to itself, okay, so remember, it's sort of like having a function that changes a real number to another real number. Okay, so domain is the same. We pick an n-dimensional vector, we're changing it to an n-dimensional vector, which means that the matrix corresponding to this is going to be a square matrix. Well, it turns out that the following properties are equivalent. Okay, so in other words, if one of them is true, the other ones are true. And no, this is not like the Monster theorem, it's much shorter. Okay, so the first property is that T is one-to-one. Okay, so if T is a one-to-one linear transformation that changes n-dimensional vectors to n-dimensional vectors, it turns out that T is also onto. Okay, I'm not going to show you the proof of this because it's very simple proof. It's a surprising thing. If it's one-to-one, it looks like those two properties are totally different, but it turns out that if it's one-to-one, it's got to be onto as well. And what I would like you to do is, again, the proof is not very complicated. I want you to challenge yourself to do it as an exercise. Okay. Now, however, I said these are equivalent, which means that if T is one-to-one, it is onto. It also means that if T is onto, it is also going to be one-to-one. Okay. In other words, it means that I can go back and forth between the two copies of Rn, and so we say that T is also going to be invertible. So this is the third equivalent property. Okay. So if T is one-to-one, it means that T is invertible. Okay. By the way, I haven't talked about in the class here about a linear transformation being invertible. You know what that means from calculus. You also know what it means to be invertible for matrices. Do you think there is a connection there? Well, I'll start thinking about it. We're going to look at that in class. So going back to this equivalency, so a function that is one-to-one, sends different vectors to different vectors, is going to be onto. And if it's onto, it's going to be invertible. And if it's invertible, it's going to be one-to-one. So all those three combinations are going to be equivalent. And one of them is going to imply one of the others. And here is another one. The matrix of T has a non-zero determinant. Okay? That should be familiar to you, should be a non-surprising thing. If T is invertible, its matrix has to have a non-zero determinant. Why? Well, because the matrix is going to be invertible, right? So the last equivalency should be fairly clear. The first two may be a little bit more surprising, and you may want to work a little bit with them. Now, if a transformation has any one of these properties, and remember they're all equivalent, then we're going to say that T is an isomorphism. Okay, so each vector, well, we know already Rn is isomorphic to itself. we know that Rn is isomorphic to itself according to our old definition, right? We say that two vector spaces are isomorphic if basically the only thing that changes is the name of the vectors. Well, here that doesn't even change that. But now we're assigning the name to the function that describes that correspondence. Okay, so if we're gonna say that a linear transformation of Rn to itself is an isomorphism, if it's 1-to-1, it is invertible, is onto, it basically just changes, twists around the elements of Rn into different ones, but without really stretching, cutting, or squeezing or squashing the objects that it is dealing with. Later on, we're going to extend this property of isomorphism to other vector spaces, and therefore we'll have a more formal way of checking if two vector spaces are isomorphic.